Asian small-clawed otter, right? And so what we're going to analyze is simulated otter data from South China. And the way that this data is structured is we have these rivers. You have first order, second order basins, and as you go up the mountain in elevation, you have all of these rivers branching. You have variation in the width of the river. You have variation in the elevation of the river, and we're trying to estimate the occurrence of otters across these rivers and what might be driving their distribution across these sites. And so I'm going to try to do the whiteboard here. So what we have is, this should be fun, a river, right? And you can see that in some area, everyone can see my river?
Yes.
So we have these rivers, and you can see the width varies. And what we have is we have a site. We're calling it a site, and it is a stretch of river that is 600 meters, right? 600 meter stretch, and it's broken out into three 200 meter segments. And each segment, we put a camera trap. Man, I'm getting good at this. Okay, and so we have the camera trap on the river's edge. We're shooting it into the water, parallel with the water, and we're trying to detect otters in our site. So in this case, our repeated surveys are spatial, right? We have a 2 meter segment of river here, 200 meter segment of river here, here, and here. So our survey data looks like this. And then, so for example, we have another site, and then we have 2 kilometer space, and then we have another site. Right? And then we have our cameras again. So this is what the data structure looks like. Now, so let's look at what those data look like. So we'll open the Otter CSV. And what you can see is we did all these surveys. We set these camera traps at those 200 meter intervals, and each row is a site, and each column is our survey, right? So row 2 is site 1, right? And we had our 3 cameras. We did not detect an otter from camera 1, from camera 2, or camera 3. Survey row 3, site 2. We detected an otter at the first camera, not the second, not the third. And so that's what all of that data structure looks like, right? All the way down to, we had 77 sites. Does that make sense? We have repeated presence, absence. Oh, shoot, I'm not sharing my screen, am I? Well, I'm assuming everyone's looking at the Excel. And you see what we're looking at is that is our repeated occurrence data. And then if we open Otter Covs, let me share my screen here. What we have is a couple different things. We have width 1, width 2, and width 3. Remember, our camera is facing the river, and otters are swimming back and forth in that river. But if a river is, the variation in the river width can be quite large, right? So this river width is 1,148 meters wide, whereas this river width is 352 meters wide. Now, camera traps can't detect all that far, right? Maybe they can, but you have to assume that perhaps the river width is affecting our ability to detect otters when they're swimming by. So, and it might also affect their occurrence in the rivers. So perhaps they like wider or narrower rivers for some reason that we'll think about biologically. If you could delete this with the Z column, because that doesn't make sense yet. And then the other covariate we have is elev, elevation, right? And so this is right now a standardized covariate where where it's standardized to range between -3 and 3, right? So the average, the mean is 0, and we have 3 standard deviations from 0 and negative from 0, and 3 standard deviations positive from 0. So all that this means is that the positive increasing numbers are higher elevation sites, and the lower decreasing negative numbers are lower elevation sites. But remember, we just said that maybe otters are choosing their sites based on the river width. Now, the thing is, we have 3 river widths, depending on where the camera is, for our site, right, which is the conglomerate of those 200-meter segments. So our site in this instance is a 600-meter river run separated by greater than 5 kilometers from the next river run. So maybe what we want to do is actually take the average. So we'll do equals average of those 3 widths to get a site level covariate. Because if you want to try to estimate the effect of river width on the occurrence of otters, how are you supposed to choose which one of the detection widths is the driver of the otters? Because you could see there is some variation. At site 2, you have a 350-meter wide river stretch and a 1,000-meter river stretch. It's one of these buckled out waterways. And so what we'll do is we'll call that width underscore site, right? So now we have a mean width across our sites. And what we could do is, I could just show you how we'll standardize that, but we'll actually standardize it in presence. But what you would do is you would calculate, I'm not going to do it right now, but basically to standardize a covariate, what you're going to do is have the value minus the mean divided by the standard deviation, and that will get it into this scaled parameter space like elevation. Right now, we're just going to leave width site the way it is. So does that make sense? Cool. So now, let's just come up with a couple hypotheses. In the group chat, as I'm going through, could you please each, write in some biological drivers that we're all Asian small clawed otter experts. We're going to run these models. We know what's driving their distribution. We want to figure out where they occur. What are some potential drivers? So I'll start. We are the biological drivers, right? So I'll start. So since we already have, we only have 2 covariates, right? We have elevation and we have width of the river. Unfortunately, I didn't have enough foresight to collect a whole bunch of other data, like maybe how many fish there were across the sites, or maybe how many fishermen there were across the sites. But we could maybe account for some of those things with the covariates we have. So my hypothesis is that as you go up in elevation, you expect to find more otters because human development is largely associated with downriver ecosystems, right? Lower elevation sites along rivers. And so my hypothesis is that there are fewer fishermen and fewer direct effects of boat traffic and urban runoff at higher elevation sites. And maybe that's what's driving the distribution of Asian small-clawed otters. Now, if anyone else wants to add some hypotheses of things maybe we should consider measuring next time, or what might be another hypothesis, please just feel free to write those in the chat, and we could think about those things. So Monica suggested that there would be more otters, or otters are the probability of otter occurrence is going to increase in wider rivers because there's more habitat for fish. So you can see how we have two simple covariates, but they might account for some of the biological things that are driving the distribution of otters. So again, please feel free to write some more of those possible covariates in the chat there. So now what we're going to do is we're going to open presence. Let's see. Okay, so let's open present. And we're going to go to File, New Project. So the problem is the screen sharing isn't great because okay, cool. Vicky put an interesting hypothesis, right? Occupancy increases in wider rivers, but detection might go down because the area is too large to get adequate pictures. That's a great theory or idea. So I just want to share screen. So can you guys see my my presence window, hopefully?
Yeah, we sure can.
Okay, cool. So the black box is running all the guts of the models, right? We're just going to lower that. So we're going to start a brand new data project, and we're going to go to input data form. And you can see that we have the number of sites, number of occasions, number of site covariates, number of sampling occasions. So we're going to go to input data form, and it's going to generate a little data form that we could paste our data into. And so how many sites did I say we had? 77, right? We had 77 sites. How many surveys? We have 3 spatial replicates from each site. So the number of columns is going to be 3. The number of surveys per season, well, we only have 1 season worth of data. We only have 1 method per survey. And then we'll add our site covariates. We have how many site covariates? We had 2 site covariates, right? And then how many sampling covariates did we have? We recorded river width at the 3 different sites, right? But river width is only 1 sampling covariate, because watch what happens when we add 1 sampling covariate. We look at our sampling covariate tab, we only have 1 sampling covariate, but it can vary with each survey occasion, right? Whereas the site covariates are static. you can only have one measure, the sampling covariates can vary each of the 3 different surveys. So now we're going to go back to our presence absence tab, and we're going to go to our Excel of Otter CSV, right? And what we're going to do is just simply copy and paste our row 2 through 78, right? And we're going to copy. And we're just going to go to presence absence data, make sure we're in the presence absence column, and we're going to go to edit and paste values. Okay, now in presence, our presence absence data, all of our survey data is in, right? 0, 0, 0, 1, 0, 0, all the way down to site 77. Perfect. So now we'll go to site covs, site covariates, and we will pull up Otter covs. Now, I'm going to do this a little bit different than just pasting them both in, because I didn't standardize the width, the site width, right? So we have site width, right, which is our mean width across our 3 repeated surveys per site. So we're going to copy that, and we're going to copy that whole column with the title. And we're going to put that in, we're going to highlight C1. We're going to go to edit, and we're going to paste with cov name. Okay, we want to paste with the covariate name. So now you see we put in our covariates. We have our mean width for all 77 sites. Now, while I have that mean width in there, I'm going to go to edit, and I'm going to go to scale covariate. And so now we have our scaled covariate. You can see that there's actually, oh, it's a different scale than I was expecting, but that's okay. I'm not sure what scale that is, to be honest, but that's okay. It's scaled. And so now in C2, we're going to go back to our Otter covs, and we're going to copy our elevation column. We're going to highlight C2. We're going to go to edit, paste with covariate name. So now we have our scaled elevation, our scaled river width per site, and across our 77 sites. Then we're going to go to our sampling covariate, and we're going to go to Otter covs again, and we're going to do width 1, width 1, 2, and 3. And we're going to copy them with, we're going to copy them with their names. Make sure we're in sample covariates. And we're going to edit, paste with covariate names. And it gives us a chance to name the site covariate, and we're going to call it width underscore survey. Okay, I see some people are asking questions. Let's go to the chat. Oh, normalized data. The first option was normalized data. You guys are probably using the most recent presence. I think I have an older version. So whatever scale or normalize would be the same thing. And they might actually do it in different ways. But the important thing is it's just a data transformation to try to make the data fit the assumptions of a normal curve. Um, yes, I can, give me one sec. So Monica asked a question, how come width is both a site and a sample level covariate? And so remember, we can have width varies at each of those runs, those 3 runs, and it's affecting our ability to detect the otters. But width also could have a biological relevance because there are more fish in the wider parts of the rivers or something like that. And so what can happen is like what Vicky said is that we have a covariate that can affect our ability to detect them, but it could even have a negatively where we have a harder time observing otters in the wide river, but the wide river is actually the better habitat under our current hypothesis framework. And so that is just how you would account for this in those different models. And so Kenneth asked a question about how you scale it in Excel. And so I'll just show that real quick because I think we're okay on time. So in the width site here, what I'm gonna just do is go equals average. We're gonna take the average of width, right? Enter. And we get our average width of the means of the river is 630 meters. And we're going to take our standard deviation. Of those same 77 sites. And our standard deviation is 188 meters. So to get our z-score is going to be, so we'll call this width z equals the width, parentheses, the width of that site minus the mean, which is 630, close parentheses, divided by the standard deviation, 188. So this is a z-score, which is just standardizing our data to be such that the mean of our data is 0 and the plus or minus standard deviations is within 3 standard deviations. Right, so we're just fitting it to a bell curve. So if we enter and zoom down, you could see it's similar to our elevation thing, right? Where we see the really high numbers have close to 3, and the average numbers are around 0. Here's one around 0, etc. And so that's just a way of scaling it. And the reason, just to get back to the reason we scale covariates, is because it just helps fit the model better. It's not going to affect our inference because remember, this is just a data transformation and not a changing the outcome. So it's just going to help with fitting our model. Oh, the width site was just the average across the 3 runs. So now let's just confirm our data is correct. We have our presence absence data from our 3 surveys from our 77 sites. We have our 2 site covariates, the site width and the elevation. Don't worry if your site width is a little different than mine because depending on how it's, oh, I scaled the covariate, I should have normalized it. Anyway, that shouldn't affect anything too much. Normalize the covariate was how you get it to be 0 with a standard deviation of 2 or 3. So what I could do is just re-enter that real quick, just in case. anyone else have any questions? Is everyone able to follow along? So now I'm going to try to normalize that. And then we see, yeah, sorry about that. I just feel like overlooked the normalized one. Okay, so now we see our data is normalized with site, elevation, width survey. Now we could normalize the width survey too and still call it width survey. Okay. Okay, so now let me see if there's any questions real quick. Sorry, 1 second. So what you're going to do is now go to File, Save As, and just save it as Otter Ock or something. Otter Ock. Is there anything in the chat? Does anyone have any questions? No, we're good. Okay, let's run some models. So we're going to save our data, Otter Ock. Okay. We're going to save it as otterdat.pao. Save it someplace where you know where it is. Go save. Okay. So we should be able to X out of this. Now our presence window is going to say, okay, our title of our project is Otter Ock. We saved it here in our documents. We just want to check number of sites, 77, correct. Number of occasions, 3, correct. Number of survey site covariates, 2, correct. Number of sampling covariates, 1, correct. Okay, we're ready to run. Do we want to run we create a project? Yes. We create a new folder? Yes. This is great. I already have a project. I will overwrite that. Okay, so now we're in our dashboard. We're finally going to run some models. So here is going to be our output where we see our model comparisons across our different hypotheses. And remember, we have the AIC, the delta AIC, the weight, the model likelihood, number of parameters, and the -2 log likelihood. So the main things we're going to be looking at are the AIC, delta AIC, the AIC weight, and the number of parameters. And so we're going to go to run. And I just want to show you all the incredible different types of models that you can run in Presence. You can run simple single season, multi-method, false positive, multi-state, correlated detections, two species correlated detections, repeated count data, which is the N mixture model, heterogeneity, which is the Royal-Nichols model, staggered entry, all different types of models. And then you could even do those all in another multi-season level, where you look at extinction colonization rates between those period seasons. So let's, we're just gonna run a simple single season occupancy model. And a couple different windows come up. We have our design matrix and we have our model setup, right? So let's go to the design matrix. Remember, we have two parameters of interest. We have psi, occupancy, and we have detection probability, P. So we have detection probability for survey 1, camera 1, survey 2, camera 2, survey 3, camera 3, right? And so by including these all as one column, 1, 1, 1, 1, 1, we are assuming that probability of detecting otters is constant across our 3 cameras. Doesn't change. There's no heterogeneity. And when we go back to our occupancy tab, we see psi equals 1. Our assumption is that the occupancy probability of otters across all of our sites is constant. Doesn't change. There's no heterogeneity. So what we're going to do is we're just going to run this simple model. And we're going to call it psi dot p dot, right? So it's already called that. We're all ready to run. This is essentially a null model. And the assumptions of our null model is our probability of detecting otters is constant over space, and the probability of otters occurring across our sites is constant irrespective of different covariates. Oh, yeah. Okay, so let's, we can go to OK to run. And it runs it really fast because it's a simple, very basic model, right? So it says our model ran, we have our AIC, we have our number of parameters, 2, right? P and psi. So we'll add it to our results. So we've already run our first occupancy model. And so we have our our AIC and our delta AIC. Now note that our delta AIC right now is 0, 0. That's because we ran one model. And so right now, our best model is the one that we ran. So we'll right mouse click on that and we'll view our model output. And so we can look at some of the input data. So we have the number of sites, number of occasions. And then here is an interesting one. Our naive occupancy estimate is 0.4156, right? And so our naive occupancy estimate is the proportion of sites that we detected otters at without accounting for the probability of detection, right? And then if we scroll down, we see our beta estimates, right? Right now, our beta estimates are simply intercepts, right? Because they're constant. So it's just a line and a y-intercept. And if we look at the individual site estimates of psi, it's constant across all of our sites, right? So our estimated probability of occupancy across our sites is 46%, with a standard error of 0.0659. And our confidence interval between 33% and 59%. So you can see our detection probability, we have about a 50% chance of detecting otters given that they're present with our survey design. Excuse me. Okay, does that make sense? Has everyone got that? So you can see that our naive occupancy estimate was what, 41%? About 41% of our sites. But if you look, our detection probability is only about 50%. So when we account for that, we see that we missed our estimate of psi is really almost 50% now, 46%, right? So let's X out of that and let's try another model to account for the heterogeneity across our sites. So let's try a detection covariate. So we'll go to our design matrix and our detection window. Now let's remember our hypothesis was that as the river widens, your area of detection with your camera along the river edge decreases, right? Because basically as the river narrows, it might funnel the otters closer to the camera and you might detect them more frequently. So what we're going to do is we're going to right mouse click in there. We're going to add a column. And that is going to be our, we leave beta 1 there, right? Because that's our intercept. We're never going to get rid of our intercept. To make a line, we need an intercept at the y-axis, right? So beta 2, though, we're going to highlight that. We're going to go to init, and we're going to go to individual covariates, and we're going to go to, what was it? Width survey, right? Because we want the individual width of each of those 3 survey cameras. So now what we're going to do is we're going to run a new model. And we're going to call, and remember, occupancy constant, right? 1. So right now, we're going to run a new model. It's going to be called psi constant P, psi dot, occupancy is constant across all our sites, P width. So now we have detection, width of the survey with our intercept, and the occupancy, just our intercept. So we're going to go OK to run. We're going to add it. And we're going to see all of a sudden our river width model is our top model, has the lowest AIC value, has a delta AIC of 0, right? Because it is our top model. And it's much better than our constant model, better by 6.64 AIC points, right? And so this means that river width does seem to have an effect on our ability to detect otters. So let's go to view model output. Remember, our naive occupancy doesn't change, right? 41%. But now we have our betas, and our betas are going to be interesting. So our psi is still just constant, right? So the beta is not all that interesting. It's just our intercept. Our beta 1 for P1 is not all that interesting. It's just our intercept, right? But our beta 2 is the parameter associated with the river width. And so we can see our estimate here is negative 0.616 with a standard error of 0.217. So that means as the river width increases, we see a negative association with the probability of detecting otters. So we see that it's harder to detect otters when the river is wider. And so once we account for that, we see that the psi doesn't change much, right? We're assuming constant psi. It's 0.47. I think before it was about 0.46. But you can see our estimates are for detection probability are widely variable and site specific because they vary depending on the width. So we have P1. P1 is, right, our site estimate, the probability of detecting an otter given it's present at camera 1. We have to scroll all the way down through those 77 sites to get to P2, right? Our probability of detecting an otter at site 1, survey 2, given its width, right? And then down to P3. Does that make sense? So each individual site is going to vary depending on the river width because it's a continuous covariant. So now what you can do, you can actually hit this little icon here with a green arrow to just run the model again. So now let's try one more thing. Let's try detection. Let's right mouse click. Let's add 2 columns. Obviously river width is an important one. We're going to go to init. We're going to go to individual covariates, width survey. But what about adding elevation? So what could be our hypothesis there? Detection probability is driven by 2 things, right? Our ability to detect a species given that it's present, but also it's also associated with, for example, the number of otters at a site. So if you have a camera and you have 5 otters at a site, you have a higher probability of detecting a single photo of an otter than if there was only 1 otter at that site moving back and forth, right? So maybe our interest here is that our ability to detect otters decreases as the river widens, but maybe it increases because our hypothesis is that there are more otters at higher elevations. So let's run this model. We'll do psi is still constant. We're assuming occupancy is still the same across all our sites. P is going to be width plus LF. Okay, So psi constant, just intercept, detection intercept plus beta 2 plus beta 3. And we'll go OK to run. And we're going to add that. And look, that is even better model. I promise that it's not every time you add a covariate, a model gets better. But in this case, this is interesting, right? So our delta AIC, our AIC value is significantly lower than the others. So let's look at the output of that model. So once we look at this, what we see is we have psi constant, our intercept estimate. We have our P estimate, our intercept. You see the probability of detection given survey width is still negative, still significant. Decreasing effect, our ability to detect otters decreases as the river widens, but our ability to detect otters increases with higher elevation, and it's quite significant, right? That's a large covariate effect, such that what we see is we actually have a much higher estimate of psi, but a lot more of uncertainty now, right? Given that we're accounting for the detection probability. So that gives us a little bit of inference, but we really want to get inference on what's driving the occurrence of the otters. We looked at what's driving their detection. Now let's look at the occurrence. So we'll run another model. We should add an occupancy covariate, right? So now let's add, let's go to the occupancy tab. We'll add a column, and we're going to add elevation. Actually, let's just add both of our covariates. Let's run what's called a global model, where we're going to add all of our covariates to a model. So remember, in our occupancy tab, we can't add width per survey because that's variable in 3 different space periods, right? But we can add our width site, which is just our average across those 3 camera surveys. Then detection, what we're going to do is we're going to add our 2 columns again. We're going to go to init. Now this one we do put width survey, right? And we put width, and then we put elevation. So now we have a global model. We have the probability of otter occupancy is related to elevation plus width, and our probability of detecting otters is related to elevation plus width. Right? So now how many parameters are we estimating? We are estimating 1, 2, 3 for occupancy and 1, 2, 3 for detection probability. So we called our model. Let's run it. Now, lo and behold, we have our new best model, right? So let's look at those output. Okay, so here's where it's a little bit interesting, right? So now we have our probability of occupancy is strongly associated with elevation. The higher you go in elevation, the higher the probability of otter occurrence. But as the river widens, we see some negative association with otter occupancy probability. But if you look at that estimate, it's highly variable, and the standard error is basically the same as the estimate itself. Now for P, you see that there's still a strong effect of a negative association with river width and detection probability, but a less strong effect now that we're accounting for elevation driving the occupancy parameter, but it's still a positive association with elevation and detection. So now that gives me the idea, maybe we should run an elevation only occupancy occupancy model. Actually, what you can do is you can hit retrieve model. You can retrieve the top model, and that pulls it in here, right, with our detection covariates and our occupancy covariates. And all I'm going to do is right mouse click and delete that column with width. And now we're just going to call it psi elevation PLF plus width. And we're going to run that. And check it out. We have a better model. Now, it's still within a relatively small delta AIC. It's less than 1 delta AIC different, but it's still a better fit in terms of parsimony, less parameters to estimate. And we see that, again, our occupancy probability is strongly positively associated with psi. Our probability of detection is negatively associated with river width, and our detection probability of otters increases as we go up in elevation. And we see all of our site-specific estimates of psi given the elevation. So you see that the probability of site occurrence at site 1 is 85%, very high, right? Given that it's high elevation. And so, so there are still a couple other parameters models that we could run. We could compare a couple different variations of those covariates. But right now we have our top model. And so we just have to think about what that means biologically for otters. We came up with a couple hypotheses that maybe elevation is an index of human disturbance, or maybe elevation is an index of fish abundance, where there are more fish at higher elevations, or something like that. Or maybe, the otters, maybe the higher elevation areas have more mollusks or something like that. And so these are all things that could be driving these patterns, but we used a very broad scale to estimate them. And so maybe now we ran our first, this is where kind of adaptive sampling, adaptive management, and our ideas for what we want to do next come from. So this was our first survey. Maybe next year, when we go out and sample again, we'll actually do a dip net and catch some fish and estimate how many fish there are as a covariate across our sites. Or we'll take a densitometer and look at the density of canopy cover over our river sites affecting that. And then we could just, or what we could do is even go back and look at remote sensing data. And instead of using elevation, we could use some remotely sensed data, for example, the human footprint index, or the density of houses or buildings or development, and measure those as potential covariates in driving occupancy. So, so right now it's 12 o'clock. We're going to, please